Sorry. Hello. Yeah, sorry. Okay, now maybe it's a little too much, but okay. So so basically, we have this constraint, and this also allows us to set constraints on the essentially the volume density of ionized hydrogen. Pierre showed this earlier, and there's a lot of other similar constraints. And there's also a constraint on the ionizing emissivity at redshift 3 to 5 from various Lyman alpha 4 studies, and as encompassed by this Becker and Bolton contour region right here. And so how does one, what constraints can one get? And this just shows you what we get, and I'll just step you through how you can get these constraints. You can put them in one by one. Basically, this is the constraint if you assume that the universe reionizes by redshift 6. Actually, this would all be red. This is just the region allowed by my models. Basically, if you suddenly introduce the Planck optical depth constraint, then 68% confidence interval starting to be here. Then you can start including other constraints, basically the constraint on the prevalence of Lyman alpha at redshift 7, basically setting a similar constraint at redshift 8 from the Schenker study, and then basically requiring that the evolution be continuous with the Becker and Bolton study is roughly as follows. Then you get this. You can try to add 95% confidence intervals, sort of like this. Then you might ask yourself the question, how do these compare with these wonderful emissivity models from Brant Robertson? This shows you his model, which you would obviously expect to fall within the 68% confidence intervals, because, I mean, it's a good model. So, and it's actually, he has a little bit of, he has some spread to this as well, but I didn't show that here. I need to check the normalization on Piero's model, but the redshift evolution is roughly as follows, and it basically fits within the 68% confidence intervals. Again, the nice thing about this thing is it's kind of, it's model independent in the sense that it doesn't really depend on the nature of the source. It tells you something about the emissivity, the ionizing emissivity. So you can kind of, it's a nice general way of trying to treat, trying to put everything under a tent. You can also try to see how this depends on the clumping factor. So you can repeat this exercise for different clumping factors, and you can see, as expected, the contour changes. So that's kind of nice. And it turns out that if you actually calculate how this changes, it basically changes as a clumping factor to the 0.3 power. It doesn't change this clumping factor to the first power, which is basically the case for a photon-starved universe. So the evolving clumping factor is not too different than these things. So basically, a clumping factor evolves from 1 to 3 is basically very close to 2.5. So evolving clumping factor is not too different. So what you can do with this whole analysis is it basically allows you to essentially set put together a banana diagram with 68 and 95% confidence intervals from these various constraints, basically reionization at redshift 6, the Planck constraint, various constraints from the Lyman alpha emitter searches at high redshift. And Brandt's model fits right here on this thing, which is not too surprising because, again, it's a good model. So now let's see. So now, what can we fit this with various populations? So we have a constraint on the ionizing photons as a function of redshift, which is independent of the source of the photons, largely. I mean, there's still some model dependencies. So what population of source can explain this? Let's see. So basically, let's say galaxies do this. So how fast would this density of ionizing photons change? And so you can just very simply just integrate down the luminosity functions, and this is the result you get. Obviously, we know that when you integrate this up, the luminosity function probably extends fainter than that, so maybe it extends to -13. There's been a lot of discussion of that. And so you need to apply a little bit of a correction or extrapolation. And so here is the result to -17. Here's it to -13. And so how do these things compare? If you compare the ionizing emissivity evolution to galaxies, basically you get this for galaxies. You can see the evolution is actually very, very similar. This is just for one normal escape fraction or photon production efficiency. You can actually very easily assume different values for the escape fraction or the photon clumping efficiency. However, those things wouldn't really correspond, wouldn't fit very well, because you need these two contours to essentially overlap pretty well. And so, maybe that works better. Anyway, so basically, all doing this whole exercise, you can basically derive a constraint on the conversion factor from UV light to ionizing emissivity. This is basically a photon counting type exercise. And so basically, from this whole thing to set the normalization, it's basically a product of three things. Obviously, escape fraction, production efficiency, and basic correction factor of the faint end slope. And you get this, which is basically the same as preferred by the Robertson 2015 model. So maybe not too surprising. But another thing that's nice about this is that you can actually, so one other thing about this constraint is you can actually fold in the clumping factor into this as well. So you can see how the clumping factor evolves, how it moves. And so basically, you can also add in a clumping factor into this whole thing. So we basically know that this whole thing is equal to this conversion factor. And also, there's an uncertainty. You can calculate an uncertainty based on the uncertainties in the ionizing emissivity and UV luminosity density. So you basically have this. And in essence, I think this is one of the main lessons we can get from all these sort of analyses. And all the things that you do with the luminosity function basically just provide you with constraints on the escape fraction. Or basically, M limit provides you with constraints on the escape fraction. So again, this has sort of been shown in Brandt's paper, but basically, it's interesting to compare the constraints on the ionizing emissivity from Planck and WMAP. Here was the WMAP constraints. Here's a Coulin et al. Model. Basically, this is a nice model by Piero, Hart, and Maddow. And here's what you get from just from Planck. Okay, so that's first part. I don't know how much time I have, but if possible, I'll just tell you a little bit about Redshift 9 to 10. I know lunch is coming soon, but let's just talk about science, what some things you can do now with some of the new data sets. You can find large numbers of redshift greater than 4 objects, both from very deep surveys and from very wide surveys, basically all of candles, for example. And from these data sets, here's, for example, the number of redshift 7 galaxies as a function of luminosity. Here are the numbers, 5 candles fields. Here are the UDF and various parallel fields. Basically, you add these things up, 480 sources. If you include the frontier fields, all the sources we have from those, the deep frontier field program that was talked about this morning, you get up to 640, 80, 64. And then if you include in Redshift 8 objects, you can get up to 1,000. So this differs dramatically from the situation at Redshift 9 to 10. This is basically over a year ago. This was the situation. Basically, we had a relatively small number from candles at Redshift 9 to 10, and this was the situation from the UDF. Again, not too many, basically 12 objects. Fortunately, we've been working hard to improve this situation. So a very exciting discovery early, a year and a half to 2 years ago, was the discovery of very bright galaxies over the Goods North and Goods South field. Here are the 6 objects found by Pascal Oesch. And we've been working to improve that by folding in galaxies at redshift 8.5 to 9. The previous samples were mostly of 9 and above. These are basically including 8.5 to 9. So now we have more than 10. We're also trying to fold in the other candles fields. Here are these other fields where there were previously 0 candidates. Fortunately, we've been essentially taking advantage of the full set of HST, Spitzer, ground-based, and optical near-infrared data to really identify the best candidates. And here's a set that we identified. We submitted an HST proposal to follow these things up. It was approved. And so we targeted all these sources for, with follow-up HST observations, relatively small 11-orbit program. And basically, after getting the deep HST observations, we got the observations at just the right wavelength to make these candidates as robust as possible, just blew over the break. And so these are the sources we came up with. So we have 5 more redshift 9 to 10 candidates. So in general, we have 15 in total candidates overall. Obviously, the bright end isn't the only place, and we're also interested in finding faint redshift 9 to 10 candidates. And so we've also been doing a lot of work there. And so there's basically 30 more candidates. Here's our, this is all in prep, but this is pretty much pretty close to our final compilation. And if you add all these things together, this was what previously was available. Here's including the bright and the more faint objects. And here's folding in the frontier field program. So basically, we're looking at over 40 redshift 9 to 10 candidates already. So we're starting to get to statistical redshift 9 to 10 samples. And so what do you derive, for example, for the luminosity functions? Here is basically the luminosity functions we derived basically a year and a half ago, where we basically tried to essentially fold in all candles data sets, UDF, and some other fields to basically constrain them at all redshifts. We've been trying to upgrade this by basically folding in redshift 9 and then folding in the frontier field. So basically trying to effectively use all HST data to constrain the luminosity functions. Here are the results. Basically so far, this is still preliminary. Basically the final was basically from redshift 4 to 10. And so these are the constraints. So we're basically, should be pretty state of the art. This is not some prep, but basically only one really, aside from these studies, to really go down to -17, which is what you can do with the UDF, folding in this, and basically 2.5 times more very wide area data than the closest competitors, so at least with HST. So let's look at the science. What can you do with the science? One thing you can do with the science is just look at the steepness of the luminosity function and just look at the feign end. And so you can see that the feign end slope is obviously changing pretty dramatically. And you can try to quantify this by deriving the feign end slope as a function of redshift. Here's out to redshift 8. Here is essentially folding in some, I still need to get the actual error bars on this. These so basically at redshift 9 and 10, basically assuming we need to, it's difficult to completely get down the M star value, but that's basically assuming that. And so it basically shows a steepening of the luminosity function. It's completely consistent with the evolution of the halo mass function. The halo mass function also steepens at this effective luminosity range. And so it basically predicts this evolution. You can look at, one other thing you can look at is how does the evolution of the star formation rate density evolve with time. It's basically what we get here. This is Pascal's, some preliminary results from Pascal. This is some of our results. This is how things evolve, including all 4 frontier field clusters. It seems to be things are continuing going this right way. So finally, I'd just like to quickly say something about what we can, a simple model to understand this entire evolution. What can we say from all of this? How can we understand? We got these luminosity functions that look great. What can we infer physically from this? And so it's nice to just compare with the halo mass functions. So how much the halo mass, how much galaxy halos light up, how much they acquire luminosity to reproduce these luminosity functions. And I'm just going to present a simple model. It's not the only model, but it's a model that we think fits pretty well. It's basically just to start out, let's start out with luminosity traces mass. And so, this is just, this is a luminosity function. Here is basically the halo mass functions, just assuming luminosity traces mass, fixed mass to light ratio. And let's see how things look. So how can we make things look better? How can we make things agree? And I'm just going to say some pretty simple things, which I think roughly work. So basically, first thing we can do to make things look better is to make the high redshift halos brighter. Basically, this sort of suppresses the evolution, and it also better masses UV luminosity. What might motivate this? You could basically just assume that star formation is more efficient, the time scale is less. And so if you do that, just basically make that happen. Now the situation looks as follows. We just basically assume that star formation in the high redshift halos is more efficient. Now what else can we do? You can see the feign end slope here is a bit too steep relative to the observations. So let's fix that. Let's assume some supernova feedback, and let's assume the supernova feedback is basically time independent and is such that mass to light ratio, actually this is probably, that should be a minus. Okay, so I put that wrong. That should be a minus. So basically the mass to light ratio is higher for the fainter galaxy, so yeah, there should be a minus there. Okay, yes, I need to be done. Okay, so that basically gets that. And so then at that point, you can see things look pretty good, except at the bright end. And at the bright end, you see you need to basically introduce a cutoff, maybe quenching or dust extinction, things like this, maybe inefficient star formation. And you can just introduce this at a fixed halo mass, just a fixed cutoff at some mass, and just assume that at some physical halo mass, things just do this. And then it turns out that things actually look pretty good at that point once you start doing all that. And you've just done some pretty simple things. And the required physics is just the follows. It's basically at high redshift, the halos must be brighter, star formation more efficient, and this can be independent of halo mass. And these following two things can be independent of redshift or cosmic time. Basically, you need to introduce supernova feedback and some cutoff mechanism, which depends on mass. And there's a lot of models which have implemented this. I'll just quickly go through the implications. Basically, if you do this sort of model, you get perfect match to the perfect match to the Feynman and slope evolution. The bright end cutoff of the luminosity function, again, you get a near perfect match to it, just assuming this sort of model. The theory implies the bright end of the redshift greater than 6 look very similar to the halo mass function, and there's been papers by Bauer et al. Claiming something like this, and basically things seem to look pretty similar to bright end. And basically, if you do this simple theory, you basically get a pretty good match to the quote-unquote accelerated evolution. And it's basically just due to the fact that we're accessing a steeper part of the mass function at redshift greater than 8 than at lower redshift. And so this is fairly similar to a bunch of models. Anyway, there's a bunch of other models in the literature which roughly gets this. And again, working on the frontier fields, which should extend this eventually. Summary and conclusions. We have this a very simple way of looking at reionization is to try to constrain the evolution of the ionizing emissivity. The growth of the ionizing emissivity basically matches the evolution of the UV luminosity density, which suggests that galaxies are the things which drive reionization. The strength of the approach is it allows us to basically ignore all parameters, various unknowns, until the last step in the analysis. So you basically push that all off until the very last step, which is kind of nice. And you can basically set all these unknowns equal to a single quantity. And you can basically, there's large numbers of high redshift 9 to 10 galaxies, more than 40 in the current surveys. The redshift 9 to 10 luminosity functions are steeper. There's the new research results suggest a slightly accelerated evolution at redshift greater than 8, and results on redshift 9 to 10 samples can basically be understood in the context of pretty simple ideas for the evolution of luminosity functions, etc. Sorry, I went a bit too long, but okay, so that's the results. I guess none of you are paying attention because you're thinking about pizza, but.
So thank you, Richard. Yes.
I was paying attention. Your second point there. Let me pivot with that. Don't.
Okay.
The growth rate of the ionizing emissivity matches the evolution of the galaxy luminosity density. I just argued, I think you would agree, that the escape fraction is going to be redshift dependent. So that redshift dependent immediately rewards that correlation, or if there is such a correlation, then it's just.
I hear your point, and it's certainly possible to still conclude that with a mild evolution.
But that doesn't work.
Okay.
The evolution as a function of redshift to explain the gamma as equal 4, and to get you the escape fraction of 20 or 30% of high redshift. You need an escape fraction that goes up as 1 plus e to the 4th power. So that's what we use. So it's a very steep function. So in other words, that correlation there, if it exists, it's modulated by the escape fraction rather than anything else. It's just a comment, Richard. I don't. Sorry?
Sentence.
No, I agree that all the stuff I was saying is far too simple, and but I thought it was kind of nice to just try to do some very simplistic analysis And just so that we could try to, for example, very simply compare Brandt's models and your models and everything, so we could
Can you show the background Bolton contours again? I think that you're doing.
I think that you're right. It does.
This blue contours that you showed from background.
Yeah. Let's go back to there. Let's go back to before. Okay.
I think that's what's going wrong.
Yeah. You can.
These are actually not error bars. There's a systematic error included, so you can shift the points up and down, but they go up and down together.
Yeah, I mean, I completely.
So hitting
I gotta get
hitting that area at an arbitrary slope will not do.
No. I completely agree with you that this is heading in a direction where we're basically, by the time you get to Redshift 2, that it's going to be in conflict. By the time you get down to Redshift 2, it'll be in conflict.
The slope is just wrong. As Pierre just told you. The slope you're getting in there is just wrong. And that's the reason why Pierre needs a redshift-dependent escape fraction to fix it.
Yeah, well, I mean, I'm not disagreeing. These are big. You're right. There are very large error bars here because those are systematic errors. I understand that the statistical errors are basically 10% of the size of the error bars plotted here. Those error bars are so big, basically, as you know much better than I do, because they made some very liberal assumptions about the systematic errors. No, I mean it's true, but nonetheless, I think it would be useful to one could try to repeat this entire analysis of doing things the way you suggest. And if you do things the way you suggest, then it's obviously true that there may be some curvature. It would suggest there's some curvature here, and that would imply an involving escape fraction. I don't disagree with that. I agree there's some clear tension here.
So, I have a comment on your first slide, the reverse engineering part. So, the physics for ionization of quasars and the stars are a little bit different. For the UV part, also X-rays on quasars will make contribution in the high redshift because the power goes as 1 plus z to the 1.5 power. So if you tail, there will affect your overload tau integral, among other things. Was it clear?
Can you say it again one more?
So the topologically, even for the UV part, quasars and stars have different sizes because the abundance difference, but also in X-rays. And the stars don't have X-rays, and you're going to have a very different high redshift tail as well as different spatial distribution.
No, I totally agree. So, yeah.
I think X-rays are going to cause a small residual, ionization even at early time, when the Q due to UV it's small, but it's not a big effect on those curves.
I mean, again, I'm not trying to suggest this is the be-all and end-all and whatever. I just thought it was kind of useful to try to. I mean, I'd be interested to see what you would get if you try to work back. I was just trying to say if you could try to work back from the raw constraints and try to derive in some Bayesian way the evolution of the emissivity. I think it'd be a useful thing to do. Again, I don't suggest this is the be-all and end-all.
So more questions for Richard? Hands up. If not, let's thank Richard again.